This example, we've got a flying fox. So someone's flying down here, jumped off here, flying down there. They'll bounce off the bottom and land there. So flying fox, or a zip wire, or whatever you want to call it. And it's secured at each end by a 1 meter cubed concrete block. So it's got all sides 1 meter. Based on the overall stability of the block, sliding or overturning, what's the maximum allowable tension in the cable? So first step is always just to draw a quick free body diagram and get on all the forces we can think of. And so we've got a force due to tension in the cable, and I'm drawing the top block here. It wouldn't matter, it's 35 degrees top and bottom. Might not be, might have to analyse both of them to see which one would be critical, but in this case it's 35 degrees for both of them, so we can just grab one of them and check that. If it works for one, it'll work for the other, because the tension in the cable is just the tension in the cable. So what we call this, we'll call this T, say. Then what other forces are we going to have? We're going to have the weight of the block, W, say. We're going to have a reaction from the ground upwards, and it's definitely, so you can see that this force is definitely going to try and pull this block this way, and so the reaction is going to have to be in this direction somewhat, I would have thought. And so that should be, that T should be blue under my usual color coding system. So I usually put my applied forces in blue and my reactions in red. You don't have to. So this one here would be N, normal force, and then we're going to have a force of friction, and we'll just call it F to start with. We'd only call it Fs if we were talking about the static friction, so the maximum value that can be. So that's going to be F. Right. I need to give that a name. We'll call that W. Then we can just start figuring out what we know. So we're trying to find T. So that's what we're trying to find. And usually in these problems, well, not usually, I think always in these problems, best to split this up into its components. So let's call them Tx and Ty, say. What's the best way to draw these? Well, I don't have a lot of choice. And so we're going to have Tx this way, and we're going to have Ty the other way. And I might draw the Tx nose to tail up here, dotted to show that it's not the correct point of application. Tx. Now we know this angle's 35, so we'll use the Z rule, so that angle up here will be 35. And this is Ty. So then what can we figure out? We're trying to find the maximum tension. Let's just figure this out, see where we get to. So I'll just write it down now. So Tx is going to be T cos 35, and Ty is going to be T sine 35. Well, let's just calculate what those are. Cos 35 and sine 35. Cos 35 is equal to 0.8191. 0.8191, and Ty is equal to sine 35, 0.5736. 0.5736. Sorry, just checking that. Actually, that should be a 2 if we round it. Not that it'll make much difference. So we know those two, and it's times T. So we've got those now. So now we can think about some limits, can we? We could do to figure out what N is. Let's figure out what N is. Don't know why I'm doing all this blue, because my pen was blue, I suppose. Let's figure out what N would be. So N is going to be W. So we've got W down the way, and so you can figure this out from the sum of the y components must be equal to 0 for a static equilibrium. And so we've got W down the way. Well, let's just do it properly. Hold on just a second. So let's just figure out W first, because we don't actually know that. W equals M times g, which is equal to gamma times, so the unit weight times the volume. Back up there, mister. We'll just go straight to gamma times volume. We should really have said in the question that the unit weight of concrete is 24, assuming that it's 24 kilonewtons per meter cubed. But anyway, it's 24 times 1, it's 1 meter cubed. So the weight of that excuse me, concrete block is 24 kilonewtons. So that's what W is. But this time that's not the same as the normal force because it's an inclined load. So we've got the component Ty, which is lifting this block up somewhat and rotating it as well, but we'll get to the moment in the middle in a minute. So for N, to find N, we know that the sum of the Y components must be equal to 0 for static equilibrium. Therefore, Ty minus, very good, minus W must be equal to 0. Oh, sorry, plus N. Plus N must equal 0. So therefore, N is equal to W minus Ty, which is equal to 24. That's what W is. Take away 0.5736 T. So we're now starting to find some of these values. It's going to be quite interesting to find a solution to this one. Okay, now for sliding, at the limit for sliding, we are going to have F is going to become Fs, which is going to be equal to the friction coefficient times N. I think I did give the friction coefficient this time. No, I did in the real question. And so I think I said it was 0.4. And so that's going to be 0.4 times N, which is equal to 0.4. We know N, we've got that up here. So 0.4 times 24 minus 0.5736 times T. It's fair enough. And that's what Fs is equal to. Then what do we know? Well, when we're hitting that limit, it's also going to be equal to Tx. Tx is going to be equal to Fs because you need static equilibrium. You've only got two horizontal forces. So Tx take away F must be equal to 0. So for static equilibrium, the sum of the x components must be equal to 0. That means, so let's just see what we've got. So you've got positive Tx, take away, and at the limit it's going to be Fs, so 0.4. No, let's just write it out. So minus Fs is going to be equal to 0. Then we can start putting in some of the values we've got. We know that 0.8192 times T, that's what Tx is. 0.8192 times T. Take away 0.4 times 24, so I'm just putting in the value of Fs now, 5736 T is going to be equal to 0. And we should be able to solve that, I think. So we're going to get 0.8192 T, take away, let's just write it all out just in case people can't see where it's coming from, minus, so I'm just going to multiply this out, so I'll multiply both terms in there by 0.4. 0.4 times 24, 9.6. Minus that, and then it's a negative times a negative, so it's a positive, plus So we're going to have 0.4 times 0.5736 is 0.2294t, going to be equal to 0. So we are going to get 0.8192. Really? Let's keep going to see what happens. Plus 0.2294 times t. That's 1.049t is going to be equal to 9.6. So t is going to be equal to 1.049. Sorry, 9.6 divided by 1.049 divided by 1.049 is equal to 9.152 kilonewtons. We were in kilonewtons. Yes, we were, because that was the weight of the concrete block was in kilonewtons. And so what it's saying is, for static equilibrium, so the point at which it slips, you're going to have that friction is going to reach the critical friction Fs. And so we can say, and we've calculated that, we have to allow for the fact that this tension also changes that normal force. And so we had a formula for the normal force, then we've stuck it into the formula for the static friction. And we've got down through these lines here. And then we've decided we're figuring out that, look, for static equilibrium, this x component must be balanced by that, and that's going to be Fs when it's critical. So we've stuck that into that equilibrium equation, work that through, and we found out a value for t. What I'll do now is I'll just do a quick check on that. So what I'll do is I'll calculate. So if we assume this value t is equal to 9.152, we'll just check that it works out, and we end up with this value should be the right value. So let me just do a quick check on that using the numbers, and I'll pause it while I'm doing that, then I'll come back. So I've run through a check. So I've just taken that number and I've put it back into the free body diagram. I've figured out my x, and I've figured out tx and ty. Then I figured out, well, what's the normal force then? Well, it's w minus ty. That'll give us the normal force. Once we've got the normal force, we can calculate the friction. So Fs, the static friction, or the limiting value of friction. And then we can check at the critical point, this Tx will be equal to that Fs, the critical friction. And that's what we're getting to within the rounding error. And so I've worked out Tx, Ty, the normal force, Fs based on that normal force. And what we find is Tx is equal to Fs. And so that's the critical point for sliding. So for sliding, the maximum tension would be 9.152 kilonewtons. And we've got sliding here. So now let's grab this, or do we need to grab it again? Let me just copy this down just so we can see it while we're doing the next stage. Now we're going to have a think about overturning. So we'll take the critical points, pulling it this way. And so let me just move this down a fraction. So that tension is trying to rotate this block like so, like that. And so the point of rotation would be A there. And so let's try and figure out our overturning moments and such like. So overturning moment, which we're going to call MOT, is equal to, so let's see what we've got here. We've got Ty going up the way. This is, better put on some dimension. This is 1 meter. Let's put it underneath so it's not getting in the way. So that's going to be 1 meter. This here is also going to be 1 meter. So far, so good. So the moment, so let's just add up all the overturning moments. So everything that's trying to turn this thing over. So we've got ty, that's trying to overturn it. So we've got ty times 1. Nice, I've chosen 1, so we're going to make it all easy. Then we've got tx. We don't have this t acting at the same time. Split it into components, so it's not acting at the same time. It's just an alternative version of having the two components. But you've got tx. Let's just, well, it's overturning. So it's negative, but it's the overturning direction. And so I'm not doing, and this one is also negative. It's clockwise, but it is also overturning. So just ignore the negative sign. We're just saying the direction is the overturning direction. So I don't need to put the negative and positive signs in here. So we're going to have plus tx times 1. And that is the only forces that are overturning this, creating an overturning moment. We've got this one, we've got this one, that these make up that one. We're not going to count that twice. And then the only other force, so now let's just have a think about this. We'll just ignore that normal reaction. I never really talked about that actually. But what you can imagine is if this was overturning, so in fact, we're not going to ignore it, we're going to do it properly. If this was overturning, that reaction would be fully on the corner because this block is tipping up now. Oh, didn't want to do that. And so let me just move this friction. Oh, it's doing that again. I don't know why it does that, but it does. Let me drag it down, coming down. So we've done a lot of work. Interesting. So let's just move these both across. It's going to be the easiest way. We'll move this one back again. I think that's the wrong one I'm doing, isn't it? That's why it looked better. So what I'll do is just rub that out. Sorry about this. Redraw it. So it's now at the point of overturning. So we can move that reaction right back to here. That's what would happen if it was right on the limit of overturning. Your reaction would be on that corner. This would be Fs. It's going to be short. It's going to be a smaller magnitude than the normal force, though, because the static coefficient of friction is only 0.4. Yep. And so that's why this doesn't contribute to the moment, because we're imagining that it's at the point of overturning. And so it's like this. It's rotating around, and so it's only sitting on that little corner. And so it's the point at which your reactions moved right to that corner would be the point at which it overturned. So we've got this overturning, that overturning, this is restoring, and these are doing nothing because they're at the point A. Coolio. So restoring moment. MR is just going to be the weight times, well, we should probably have, just before I go on to this, sorry, we should just work through what this actually means. So that is going to be, let's just figure that out. So Ty is T sine 35 plus T cos 35 for Tx, which is T sine 35 plus cos 35, which is going to be equal to sine 35 plus cos, just a second, plus cos 35 equals 1.393. So that's going to be T times 1.393, which is equal to 1.393 T. Okay, so what have we done? We just figured out which forces are going to cause overturning, what their lever arms are. In this case, super simple because the lever arms are both 1. And then we've just put in these as components. And it's similar to what we were doing before. We are trying to get it down to a single variable so that you can solve the equation. Then we've got restoring moment. is just equal to, so we'll call that MR, it's just equal to W times 0.5, which is 24 times 0.5, which is just going to be 12 kilonewton meters. And so at the point of overturning, we're going to get this value here is going to be equal to this restoring moment. So at the point where it's just about to tip over, these are both increased far enough that they're going to be equal to that restoring moment. So let's figure out what that is. So we would have, so at impending overturning, we will have MR is equal to MOT. So that means that 1.393 T will be equal to 12. Therefore, T will be equal to, so we've got 12 divided by 1.393, which is equal to 8.614 kilonewtons. 8.614, or 5 actually for rounding, 615 kilonewtons. Now let me do a quick check on that as well. So I'll just put the numbers back in my free body diagram, and we'll just check that we are at the limit. So we are at the point at which the overturning moment equals the restoring moment. Give me a second, I'll do that. Okay, so I've worked through the check, and it is the case that if I put the value in here and calculate my x and y components and then calculate the overturning moment, it's equal to the restoring moment. So this is when T is at 8.615 kilonewtons. We're at the point where it's about to rotate. Now, then you have to figure out which one would happen first. So the rotation would happen at 8.6 kilonewtons. The sliding would happen at 9.15 kilonewtons. So that's what we're figuring out up here. And so therefore the safe load is the lower of the two. And so it's going to be that 8.61 kilonewtons, and rotation is going to be critical. So we'll just write that out. So the max tension in cable before loss of stability or loss of static equilibrium, loss of static equilibrium is equal to 8.615 kilonewton. Let's round it to three significant figures. We're at the end. 8.62, say, kilonewtons. Rotation, or overturning probably is a better way to put it in engineering. Overturning is critical. And that is our last statics example. How terribly exciting. Okay, so just a quick recap of what we did. So we had a block that was holding down this cable. The tension in the cable, we wanted to figure out what's the maximum tension, which will be a function of how heavy this person is. So the maximum tension in the cable is what we wanted to figure out. That could be anchored with this 1 meter or 1 cubic meter concrete block. What did we do? Well, we split this force into its components so we can figure out which part of that force is trying to slide the object and which part of that force is affecting the normal force. And then we calculated the mass of the block so that we could calculate also the normal force. So normal force, you just take the weight, take away any upward component of the tension or of the force due to the tension in the cable. Might have been down the way. That force, you might apply a force down the way to a block like this, in which case it would increase the normal force, which would increase the friction. Then we figured out, well, at the limit for sliding, this frictional reaction is going to be equal to Fs, which is the static friction, and we can calculate that from the coefficient of static friction. So we figured out Fs. And then we just built up a little equation using the fact that for equilibrium, all your x components must add up to 0. And we've solved that little equation to find out what tension would cause this block to slide. Then we've just taken that number and chucked it back in to check we've got the right answer. We know we've got the right answer if the x component of the force is equal to the frictional coefficient for the normal force that we had. Then we've gone back and started again pretty much, and we've just looked at the overturning moment, and we're saying at overturning it's going to be sitting on its corner like this. This is exaggerated, but it'll just start to sit up on its corner like that. So we know that that normal force must be right back at this little, at the point of rotation, and the friction coefficient will also act there, or the static friction will also act there. I've put Fs in there. That's not really true. It's just some frictional component, because we've just found out that this will start to rotate before we reach Fs, because the force from the tension in the cable that causes it to rotate is actually less than the force that would cause it to slide. And so at the point of the rotation, this is a bit less than Fs. But we've basically done the same thing. We split this up onto its components and expressed those components in terms of t so that we reduce the number of variables, just using our trig. Then we've figured out what our overturning moment was just by timesing each of these by their lever arms and just being careful. Well, you do have to be careful about direction, but if one of them was in the opposite direction, you'd add it on to the other equation. So it would be a restoring moment instead of an overturning moment. And then we know that appending, when it's close to overturning, then the restoring moment will be equal to the overturning moment. And we've used that to figure out what the tension in the cable would be at that point. And we found that that was a bit less than the tension that would be required to cause it to slip. Therefore, this is the maximum tension we can allow, because it will start to rotate at that point, and overturning is critical for this problem. So the maximum tension for equilibrium is 8.62 kilonewtons. Cool, a bit of a long example, apologies, but hey, we'll go out with a long one for the last one.